Welcome to the third outcome, all about sequences and series, the patterns that sit behind so much of computing and finance. Once you can spot how a list of numbers is built, predicting any term becomes straightforward. A sequence is simply an ordered list of numbers, and a series is what you get when you add those numbers up. In this outcome, we look at recurrence relations, arithmetic progressions, and geometric progressions. And for each, we find both the nth term and the sum of the terms. The single most useful skill is learning to spot whether a sequence adds a fixed amount each step or multiplies by a fixed ratio, because that tells you exactly which formula to reach for. Let's fix the vocabulary first. A term is a single number in the sequence, and the nth term is written u sub n. A recurrence relation is a rule that builds each term from the previous one, such as u sub n plus 1 equals u sub n plus 3. And a series is the sum of the terms, written s sub n for the sum of the first n of them. A quick way to classify a sequence is to test how it grows. 5, 8, 11, 14 adds 3 each time, a common difference, so it's arithmetic. 3, 6, 12, 24 multiplies by 2 each time, a common ratio, so it's geometric. 1, 4, 9, 16 are the square numbers, a quadratic pattern, while 1, 1, 2, 3, 5 builds each term from the previous two, a recurrence, and that's the Fibonacci sequence you'll meet a lot in computing. Let's generate a sequence from a recurrence relation. We're told u sub 1 is 5, and each new term is u sub n plus 1 equals 2 u sub n minus 1. So u sub 2 is 2 times 5 minus 1, which is 9. U sub 3 is 2 times 9 minus 1, 17. And u sub 4 is 2 times 17 minus 1, 33. That gives 5, 9, 17, 33, with every term leaning on the one before it, exactly how an iterative loop would compute it. Here's the most famous recurrence of all, the Fibonacci sequence, defined by u sub 1 and u sub 2 both equal to 1, with each later term the sum of the two before it. So u sub 3 is 1 plus 1, 2. U sub 4 is 2 plus 1, 3. U sub 5 is 3 plus 2, 5. Carrying on gives 8, then 13, then 21. So the sequence runs 1, 1, 2, 3, 5, 8, 13, 21. These relations model growth everywhere, from rabbit populations to file structures and financial forecasts. Let's name the main families you'll deal with. An arithmetic sequence adds a fixed common difference d each time, like 3, 7, 11, 15. A geometric one multiplies by a fixed common ratio r, like 2, 6, 18, 54. Some sequences are convergent, meaning the terms close in on a limit, which happens in a geometric sequence when the size of r is less than 1, while others are divergent, growing without any bound. Knowing the type is what tells you which formula applies. Let's formalize the arithmetic progression, or AP, which adds a common difference d at every step. Its nth term is u sub n equals a plus n minus 1 times d, where a is the first term. For the sequence 3, 7, 11, 15, the first term a is 3 and the difference d is 4, so the 10th term is 3 plus 9 times 4, which is 3 plus 36, giving 39, and you never had to list all 10 terms to get there. Now let's add an arithmetic series up. We want the sum of the first 20 terms of 3, 7, 11, 15, where a is 3 and d is 4. The formula is s sub n equals n over 2 times the quantity 2a plus n minus 1 times d. Plugging in, s sub 20 is 10 times the bracket 6 plus 76, which is 10 times 82, so the sum is 820. The nth term formula can also work backwards to find a position. In the same AP, 3, 7, 11, 15, with a equals 3 and d equals 4, which term is equal to 43? we set 3 plus n minus 1 times 4 equal to 43, so n minus 1 times 4 is 40, meaning n minus 1 is 10. That gives n equals 11, so 43 is the 11th term, and rearranging the formula found the position for us. Here's a classic. The natural numbers 1, 2, 3, and so on form an AP with A equals 1 and D equals 1, and there's a lovely shortcut for their sum. S sub n equals n times n plus 1 over 2. To add 1 all the way to 100, we compute 100 times 101 over 2, which is 10,100 over 2, giving 5,050. This is the trick famously attributed to a young Carl Friedrich Gauss. A geometric progression, or GP, multiplies by a common ratio r at each step, and its nth term is u sub n equals a times r to the power n minus 1. For the sequence 2, 3, 4.5, 6.75, the first term a is 2 and the ratio r is 1.5. So the fifth term is 2 times 1.5 to the fourth, which is 2 times 5.0625, giving 10.125. When r is bigger than 1, the terms grow ever faster, that familiar exponential behavior. Let's sum a geometric series. We want the first 6 terms of 4, 8, 16 and so on, where a is 4 and r is 2. The formula for r greater than 1 is s sub n equals a times r to the n minus 1 all over r minus 1. So s sub 6 is 4 times 2 to the 6th minus 1 over 1, which is 4 times 64 minus 1, that's 4 times 63, giving 252. Something rather beautiful happens when the size of r is less than 1. The terms shrink towards 0, and the running total settles on a finite limit. The sum to infinity is s infinity equals a over 1 minus r. For a equals 8 and r equals 0.5, that's 8 over 1 minus 0.5, which is 8 over 0.5, equaling 16. The partial sums 8, 12, 14, 15 creep up towards 16 but never quite reach it, and this only works when the ratio is strictly between minus 1 and 1. Geometric progressions turn up constantly in the real world, so let's do a money example. You save £100 and it grows by 5% a year. Multiplying by 1.05 each year is a GP, with ratio r equals 1.05. So the value after n years is 100 times 1.05 to the power n. After 3 years, that's 100 times 1.05 cubed, which is 100 times 1.157625, giving £115.76 to the nearest penny. Let's put the two progressions side by side. An arithmetic progression adds a common difference d, has nth term a plus n minus 1 times d, and a sum of n over 2 times 2, a plus n minus 1 times d, and it grows in a straight line with no sum to infinity. A geometric progression multiplies by a common ratio r, has nth term a times r to the n minus 1, and a sum of a times r to the n minus 1 over r minus 1, and it only has a sum to infinity when the size of r is below 1. So how do you decide which is which? Your first test is to look at consecutive terms. Subtract them to check for a common difference, or divide them to check for a common ratio. A constant difference means arithmetic. A constant ratio means geometric. From there, use the nth term formula to jump straight to any single term, the sum formula for a running total, and the sum to infinity only when a geometric series genuinely converges. Always pin down a and either d or r before picking a formula. Let's recap the outcome. A sequence lists terms, a series adds them, and a recurrence relation defines each term from the previous one. Arithmetic progressions add a common difference, with nth term a plus n minus 1 times d and their neat sum formula, and the first n natural numbers add to n times n plus 1 over 2, giving that 5,050. Geometric progressions multiplied by a common ratio have their own nth term and sum formulas, and enjoy a sum to infinity when the size of R is less than 1, which is exactly what compound growth relies on. That completes our look at sequences and series, from recurrence relations and Fibonacci through arithmetic and geometric progressions. If you'd like more practice, the further reading points to core maths textbooks and the worked examples on Maths Genie and Khan Academy, plus the richer investigations on NRH. Sequences reward hands-on work, so try generating a few of your own and predicting terms before you check them. Compound growth in particular is well worth exploring with a spreadsheet.